David Smith here with one more flipped classroom math video lesson. 3 tips before we start. First, remember that you can adjust the playback speed as you desire. Second, you can pause the video at any point to jot down notes or write down questions. Third, you can turn on the captions so you can read my words on the screen. Today's topic, small world unit review. So just to know, you also received a review sheet from me in class, shared on our weekly planner as well, that gives you very specific information about the pages out of the book that you should make sure that you can do, and also talks about topics and gives you some tips. So that sheet is super important for when you're studying and preparing for the unit test. What I'm going to do in this video is give you a broad overview of the things that we did. So I think the best use of this video would be to have a sheet of notes out and just jot down things to yourself that you need to do. Like if you see something go by in this video that I got that, then maybe you don't need to worry about that so much. But if I talk about, say, how we found a proportionality constant, and you're like, oh, I still don't know how to do that really well, then make a note on your sheet to say, review proportionality constants, or whatever else it might be that you need to do. Okay, so like all of these special math units that we do, they have a unit problem. So that's where we started and that's where we finished. I think just in our last class, we solved the unit problem. So the unit problem, how long to fill up the world with people? And there were all kinds of assumptions that we made to kind of put that problem in a context where we could actually solve it in a math class. And all those assumptions are challengeable, and perhaps our prediction that we finally got to is subject to all kinds of adjustments depending on what happened and what's going to happen with population. Okay, you're going to need to know how we solved it. So there's more to it, but in a nutshell, this unit explored exponential functions and derivatives along the way to developing the correct form and ultimately the correct equation that we used to predict when world population will reach that magic number, which was something like 1.6 times 10 to the 15 people. So one of the first concepts that we explored was looking at rates of change. And ultimately, we developed a method that involves derivatives for how to calculate the instantaneous rate of change at a point in time. So a lot of these problems dealt with falling bodies. We drop an object on the earth and it falls at a certain constant acceleration. So the speed is always changing. And so we wanted to find out, like, the speed is a rate of change. So for a situation where the speed is always changing, it's useful to know what is the speed at a certain point in time. Okay, so we did this in a manual method that was involved a lot of calculating. So what we did is we figured out the average rate of change for a time interval. So like if we drop a body and it falls for 2 seconds, we can calculate the average speed for that 2 seconds. And that's a valuable thing to know. The problem with that average speed is it only really addresses that 2 seconds. Plus, it's an average speed. During that 2 seconds, the speed is constantly changing. So the average speed is limited in terms of what it can tell us. So that's when we developed this idea of the instantaneous rate of change at a point in time. So what we did is we calculated an average rate of speed for a very, very short interval of time that's right next to the point in time that we want the instantaneous rate for. And those average speeds for very short periods of time allowed us to state what the instantaneous rate would be. And so we did a whole series of problems where we did that method. And falling bodies was not the only thing. We also did a runner that was constantly accelerating, and we did a few other things that were along those lines. Okay, let's talk about taking the derivative and the context that we do that process within. We did a lot of this in the class, and we used more complicated functions than the one I'm going to tell you here, but the process is the same. So this is where I'm going to explain that in this review video. Okay, so we take the derivative to find the instantaneous rate of change. Because a falling body, the speed, which is the rate of change, is always changing. It's accelerating constantly. So it's useful to know the speed at one point. And so we do that by calculating the average speed across a very, very small interval of time that's right next to the point where we want to know the instantaneous speed. So find instantaneous rate at a point by taking the derivative. So I'm going to use this equation that came up with the helicopter that was dropping a bundle onto the ground, and you had to figure out some stuff with that. So here is our function. It started at 400 feet high, and it's falling. The minus is subtracting from the height as a function of time squared times 16, subtract that from 400, and that gives you the height. This is height as a function of time. Okay? So here's a question you might see. Find the instantaneous rate at 2 seconds. So what that means is, how fast is it falling at exactly 2 seconds? So what we do is we find the height at 2 seconds, and then we find the height at a time very, very, very close to 2 seconds. And I'm going to use 1.999 seconds. And then we compare those two heights, and we divide them by the change in time, and that will give us an idea of what the instantaneous rate is at 2 seconds. Okay? So what I did here, I found the height at 2 seconds. That's just plugging in 2 for t, squared it times 16, subtracted that from 400, and you get 336 feet high. So it's fallen a little ways. Not that far yet, but it has fallen quite a bit. Okay, so then we find the height at 1.999 seconds. Very close to 2 seconds, but not quite. So I did my plug-in step, and I got my answer. 336.0639, and there's more 9s out there. Okay? So I stopped it right there just so that I could make a point with the decimals. Now to find the average speed for this incredibly small piece of time, we just divide the change in height, that's delta height, over the change in time. So I subtracted the height at 1.99 seconds by the height at 2 seconds, and I divided it by the time interval, which is 0.001 seconds. And so what that gives me is 63.9, and it's actually 0.9998, something like that, feet per second. Okay? Now, with this process, you can take, when you pull this up on your calculator and you see 63.9999, you know that that's pointing at 64 feet per second. So you need to make that intuitive leap, that as you make that time interval shorter and shorter, the number is closer and closer to 64. So you need to be able to say, for a full points answer, that the speed is actually 64 feet per second. Okay, so we also talked about tangent lines. And these three things are actually the same thing. So the instantaneous rate is the same as the derivative at that point, which is also the same as the slope of the tangent line at that point. All these three things are the same. Okay, so what I've done here is I've made a graph. This could represent our falling body from that problem we just did, where I'm graphing time and height as a function of time. Okay, so this would be the 400 in that problem, and as it drops, the height is decreasing to 0 when it hits the ground at whatever time that is. And so at t1, whatever that might be 1 second or 2 seconds like our problem, it's some time. At t1, the height is here at h1. Okay? Now I can draw a tangent line at that point, and to review, a tangent line is a line that just touches a curve right at the point of tangency, and that's the tangent line. Now here's the cool thing. The slope of this line is the same as the instantaneous rate, which is the same as the derivative. Okay? Now, the slope of this tangent line is negative. So think about this problem, this falling body problem. What does that negative mean? If you thought that the thing is falling down, so the rate is negative, it's going down on the coordinate plane, that's why the tangent line has a negative slope and the speed is actually a negative speed. I know we did the example, we didn't throw the negative on there, but technically it is there. The speed is a negative speed. Okay, so using this concept, I've marked up this function here with a, b, c, d, and e. And now you can tell me the sign of the derivative or the slope of the tangent line for each of these 5 points. So pause the video for a minute, look at that graph, and just jot down quick notes. What is the slope of the tangent line at A, B, C, D, and E? And also understand that that is the sign of your derivative. Okay? Okay, let's see how you did. At A, the tangent line looks like that. Positive. The slope of the tangent line is positive. Rate of change is positive. At B, it's flat. So there is no rate of change. The rate is 0 because the slope of the tangent line is 0. At C, the slope of the tangent line is negative. It's going down, so the sign of the derivative is negative. The rate of change is negative. D is just like B. Again, we have a tangent line that's flat, no slope, there's no rate of change. The derivative is 0. It's not positive or negative. And lastly, at E, it's just like A. Our tangent line has a positive slope. The derivative is positive. The rate of change is positive. Okay, then we looked at natural logs. And natural logs are just logs to the base E. And we've had some recent stuff on E, and you probably remember that E is approximately equal to 2.71828, and it goes on and on. It's an irrational number just like pi, okay? But it's a special base, and we'll talk about that in just a minute. So the natural log, it's just another logarithm, but it's got this base, this number E. So we could say log to the base E of A equals x. Translating this log equation into an exponential equation is just saying what power of E makes A. Okay? So that's all that is. Now, we have a shorthand for the natural log. Instead of writing log base E of x, we just write ln x. And that means the natural log of x. But that is log base E. So that's our notation for that. And actually, before I go on your calculator, you probably have two buttons. If you don't have the fancy schmancy do any base log, you've probably got two buttons. You've got a button that just says log, and this one is a log base 10. Okay, so it's a base 10 log. You don't need to do anything else. You can just hit the number and press the log button there. And then you have an ln button, and that's the log base E. So almost all scientific calculators have these two buttons for good reason. Base 10 logs and base E logs are the most common. Okay, we spent some time looking at proportionality constants, and we calculated those constants for a variety of functions. I know you're going to need to do that on our unit test, so let's go over that process. And then proportionality constants, that study and exploration led us to the number E. So we're going to get there in just a sec. So the proportionality constant is calculated in the following way. I'm just going to use this function, 2 to the x. This is our doubling function. This should be really familiar territory for you right now. So to find your proportionality constant, what you do is you pick some values of x. You find out what f of x is. So I just put in 0 for x. 2 to the 0 power is 1. And then I figured out what the derivative is at that point. So I'm not showing you that process. But what I did to get this is I probably put in something very close to 0, so 0.001, something like that. And I calculated the derivative at that point, and I got 0.693. The proportionality constant is just the derivative over f of x. So this over that. So if I put this over 1, it's just going to be that. Now, for this function to have a proportionality constant, this ratio has to be the same for every point on the function. And as you can see from my table, that's the case. So here I put in 1 for x, it spits out 2 for f of x, and if I do, again, the derivative calculation, I'm going to get my derivative at this point is 1.386, and then if I divide the derivative by f of x, again, I get 0.693. And indeed, if I put in 2 for x, blah, 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 I'm still going to get 0.693. So this function has a proportionality constant, and that is 0.693. So what does that mean? That means that if you want to know the derivative at a point, you just multiply f of x by the constant, and that will give you the derivative every time. So you can save yourself the trouble now with the doubling function because you know the PC. So all you have to do is find f of x at any point, multiply that f of x by the PC, and that's your derivative. So that saves you some time from doing the more manual method of finding the derivative. Now here's a question for you. Why do we need this PC? What's important about that? Okay, why it's important is that means that the function, the derivative, which is the rate of change, is directly proportional to the y value, not the x value, but to the y value. So that's a key step in our unit problem. Pause, think about why that's important. Okay, if you thought population and growth is always dependent on the population, which in a population equation is going to be the y value. The x value is the year. If the function predicts population, you have to put in the year for x, and it has to spit out a population for y. So the population has to be, the growth rate has to be dependent on the population because that's where the new people are coming from. How many people you have reproducing and making babies will determine your rate. So the rate of growth for population depends on the y, not the x. But we have to put in an x to get that y. So you need a function that has a PC to model population growth. Okay, a little later in the progression in the chapter, you were asked to find a base for an exponential function that delivers a proportionality constant of 1. So it was kind of an interesting kind of an exercise. So we ended up with this number, 2.71828, goes on and on. That was the E that we talked about just a minute ago. That's the number that delivers that result. I've just put a few records in my table to show how that works. So these numbers were generated by using the manual method for finding a derivative. So I put in 0 for x, f of x is 1, and then when you use the derivative calculation, you're also going to get 1 for your derivative. So how did I get this number? Well, I remembered that 2, just from the last screen, had a 0.0693 proportionality constant. So it had to be bigger than 2. I tested 3. The PC for 3 to the x generated a constant that was bigger than 1. So then I just played around with my bases until I got here. And that was my good enough answer for when I did this assignment, that my base was 2.718. That yields the proportionality constant of 1. So what I've done here is I've put in 1 for x and 2 for x. I got my f of x in there. And then I did the manual method for figuring out what the derivative, and the derivative comes out to be the same as f of x. So when we figure out what our PC is, the derivative divided by f of x, we get 1 every time. Okay. Now this is a cool base because that means that the derivative is the y value. Okay? It's not proportional, it just is the y value. So with a PC of 1, f of x equals f prime of x. And this is why this is called the natural log. And it shows up a lot of places in the world. You've seen a video in class where we talked about all of that. So that's E, and that's how you can find E using the derivative. It's a function for which the proportionality constant is 1. We also spent quite a bit of time doing various investment type problems, and we ended up developing a general equation that helps us say things about money that's invested. So our equation was like this. The amount that you have after some period of time is equal to the starting amount. That's our principal. I've defined the variables over here. It's equal to the starting amount times this expression. And what this is 1 plus the annual interest rate. And remember, if I say it's 3.4% annually, as a number that you pump into this equation, this is going to be 0.034. Okay, so don't make that mistake. I see that from time to time. It will give you bad results. How you know is if you look at your result and you see what you have, it just grew like hugely, probably not right. Something is wrong. You got way too big of an answer. Okay, so it's the initial amount times 1 plus this little term. That's the annual interest rate divided by n, which is the number of times that interest is compounded per year. And what that means is that instead of giving you some percentage at the end of that whole year, they're going to give you a fraction of that at some period earlier along. And that's nice because it's compound interest. So now they add a little bit of interest to your account, and now that interest itself is earning interest in future periods. So you want that. In fact, what banks do is they typically do daily compounding. So at the end of every day, they give you a little bit of interest, it gets added to your account, and then the next day, that interest is earning interest as well. And it's a good thing for you. So we have starting amount is P, R is yearly interest rate, N is the number of times compounded per year. Okay? So this is a basic equation. You do want that on your cheat sheet, and perhaps a little explanation of what the variables are so you know how to do the plug-in step correctly, which is all I'm going to do here. I'm not actually going to solve this one. So here's a typical problem. Say you start with $6,200. How much will you have after 8 years with daily compounding? Okay, so let's set that up. A, we don't know what that is. That's what we're trying to find. But A is equal to P, which is our starting amount, 6,200 times 1, that's our 1, plus our interest rate, 8%, what is it? I didn't give an interest rate. What should we do? Let's do 5.4%. Okay? That's our interest rate. Sorry, I left that out, but we can add it right now. So 5.4%. So turn that into a decimal. It's going to be 0.054 over n. And what's n? Compounded daily. So that's the number of times per year. That would be 365. I'm fine if you use 365. If you want to use 365 and a quarter to account for a leap year, that's fine too. Close the parentheses, and now I have this expression, NT. Number of times compounded, that's 365 times t, which is the number of years, 8 right there. Okay? I know I said I wasn't going to solve it, but actually it would be good practice. So pause the video right now and crunch that out, see what you get. Okay, I calculated it all the way out, and what I get is $9,549.77. For money problems, you always want to have two decimals because that's the cents, that's the change that you would get. Also, be sure that you show me this plug-in step, okay? That's worth a lot of points. If you just show an answer and it's wrong, I can't give you any points. That would be a 0, okay? If you just show an answer and it's right, and you're in the habit of just not showing your work, I might still deduct points because you've got to show your work. That's an important part of doing mathematics. Now that you've watched the video, take a moment to jot down additional notes, some questions for class, or a short summary of the lesson. You can also go back and re-watch the portions of the video that were a little bit challenging for you. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.